of Salento in Italy. Professor Donateo is Associate Professor of Fluid Machinery, Energy Systems and Power Generation at the University of Salento. She will introduce now a subject. We will move now from, from sun and wind to the air, because she is talking about urban air mobility. And we will learn about reducing the environmental impact of a hybrid electric power system by optimal energy management and application to urban air mobility. We are looking forward. Thank you very much.
Thank you for inviting me. I'm going to share my presentation. Hope you can see it in presentation mode.
Yes, it's perfect.
Perfect. Okay, yeah. Okay. Thank you again for inviting me. Thank you for the introduction. My speech is about, again, the optimization of a power source, but this time within a vehicle, and in particular in a vehicle for urban air mobility. So we can start from some facts about the environmental impact of transportation systems. We all know that a large amount of global carbon dioxide emissions are due to transportation. Most of them are caused by road travel, but a large part of them are also associated to the aviation field. So it's important also in this field to obtain a reduction of the emissions. How can we do this in general in the transport system? We can do this in 3 ways. By increasing the efficiency of utilization of the energy in the vehicle, by speeding up the deployment of low emissions alternatives, and also moving towards zero emission vehicles, which means an introduction of electrification also in this field of application. So I'll start my speech with a definition of what is a hybrid electric vehicles. A hybrid electric vehicles, according to the common definition, is a vehicle where 2 or more energy storage systems are both used to provide propulsion power. This kind of power system are commercially available in the road transportation, but they are being analyzed also in the aerospace field. The simpler way to obtain a hybrid electric vehicle is to connect an internal combustion engine with an electric machine to mechanically to the propeller in the case of aerospace application, or to the wheels in the case of a road vehicle. These 2 storage systems, this kind of powertrain, are the battery, which is a bidirectional and secondary energy source system, and the fuel, the fossil fuel, which is remains the main energy source. This kind of power system allowed increasing the efficiency of the utilization of energy. Why? Because it allows the optimization of the behavior of the internal combustion engines, in particular by reducing emissions at part load and idling. Also, this kind of configuration can be also avoid using the engine if it is replaced, for example, by a fuel cell fed by hydrogen. In this case, we can also introduce a low emission alternative energy transportation system and also move towards zero emission vehicles. In this scheme, the second scheme, we can see again 2 sources of energy, the battery and the stored hydrogen, while the fuel cell and the motor generator are the 2 energy converters. In this kind of systems, despite the kind of energy source and in spite of the kind of converter, we have a general problem of optimizing the power flows. And this is the goal of this of my speech, the focus of my speech. The hybrid electric power system, a large variety in terms of configuration, but also in terms of hybridization degrees, which means the share of power and energy between the two possible energy paths. We can see here some kind of systems that are used in the aerospace field, where the internal combustion engine can be either a piston engine or a turbine engine, like in this application, and also in this speech we will speak about turbine engines. In this slide, I put some data from literature about proposed hybrid electric power systems for the aerospace field that ranges in a large variety of application, from small drones to regional aircraft, and they also present a large variety in terms of configuration and degree of hybridization. But let's focus now on this particular application, which is urban air mobility. This kind of application is expected to be introduced in our cities in 2025, and is characterized by the vertical takeoff and landing capability, limited speed, and short range requirements. This kind of vehicle are used for transportation of goods, but also of people. So they include also air taxi operation. This urban air mobility is considered a suitable way to reduce traffic congestion in our roads, but also to reduce pollution by exploiting the electrification of the power system. The electrification, this kind of application, is possible even with today's batteries because of the short range of these vehicles. In fact, the battery remains the main bottleneck in the development of hybrid and fully electric power system, particularly in the aerospace field, where the reduction of the weight of the vehicle is a very important aspect, more than in the land transportation. So the why electrification and why hybrid electric air taxi? As I said, the battery is the bottleneck. So a full electric air taxi can have a very low range. So in order to increase the range, we can introduce hybrid electric concept that can allow to reduce the noise at takeoff and landing, and to reduce the carbon footprint. So another important aspect of hybridization in the aerospace field is that we can increase safety, because the electric path can be used also in case of engine failure to allow the electric backup operation. However, as I said before, the challenge is to develop a dock flight mechanics analysis tool and design techniques in order to obtain the best possible reduced carbon footprint from this kind of power system. When we speak about the environmental impact of hybrid electric vehicles, it's important to analyze the whole process of the energy conversion from the primary energy source, the well, to the wheel of the wing in case of aerospace, of course. So usually we speak about direct emissions when we consider only what happens when we drive or fly a vehicle, which means with a tank to wheel or to wing approach. In this speech, we will compare the emission, analyze the environmental impact with a well to wheel emissions, which means by taking into account, for example, the indirect emissions of carbon dioxide associated to the charge of the battery, but also of the upstream production of the fuel, the fossil fuel, which is kerosene, in the well-to-tank process. In fact, we well know that there are, if we charge the battery from our grid, we know that we have a mix of energy sources that have been used, and all of them have different emissions factors and different share of in the production of the electricity. In order to evaluate the well-to-wheel impact of these vehicles, we developed this procedure where we perform a detailed analysis of the power flows of the vehicles during a typical mission. So our starting point is the flight power request. The flight power request is a function of different aspects, including aircraft geometry, aircraft components, mission parameters, size of which component, the engine, the electric machine, the battery of the system. This kind of aspects are very critical, and the literature in the aerospace field often focuses on this aspect that can be taken into account with the static multi-objective optimization in order to find the configuration that allows the lower weight and the lower fuel, the lower energy request. However, in this application, in this speech, we will consider a prefixed power system, and so our starting point will be the flight power request. The flight power request can be generated in infinite ways, depending on the share of the battery, on the splitting of this power request between the engine and the electric machine. So we developed a detailed model of the power system that is used within an energy management strategy, and can allow to evaluate the amount of fuel burned by the engines, but also the amount of electricity used by the battery. So this speech focuses on the energy management strategy, which is, as I said before, the distribution of power requests between the two energy sources and the two converters. This energy management, this application, the application that I'll show you is represented by a vehicle for urban air mobility characterized by the presence of a turboshaft engines, two electric machines, and a lithium-ion battery. And this kind of power system, as I said before, was predefined by the partner of our project, in particular in collaboration with the Distretto Tecnologico Aerospaziale. I cannot show you the actual results because of confidential agreement, so all the results will be shown in a dimensionless way. As I said before, the starting point of the analysis, the flight power request, we considered also the possibility to perform electric backup operation. So a first starting point was the analysis of the electric power system in case of electric backup. This analysis was necessary to set the lower limits for the battery state of charge, which means the remaining amount of energy in the battery. So in this way, we can allow electric backup operation in any moment during the mission. Sorry. And also for the normal operation, we consider different missions named A, B, C, and D, which are shown here in terms of required power, P shaft, and in terms of altitude. As we can see, the duration of these missions are about 30 minutes. As I said before, we developed a detailed model of the powertrain, including a model for the turbo shaft, for the electric motors, and for the battery, but above all, different possible energy management strategies that are implemented in the supervisory controller block, which takes as input the required powered shaft in a particular time of the mission, the required speed of the rotor, and also the remaining state of charging of the battery. And so calculate the optimal distribution of the power request between the engine and the motors. I will skip on the details of these models because I don't think it's particular interest to go into the details, but I'd like to focus on the energy management strategy. The goal of the energy management strategy was to minimize fuel consumption during the fuel burned during a flight by optimal usage of the battery. The constraint in this optimization were to keep the battery always sufficiently charged to allow electric backup, both in the case of a new battery and also an aged battery. In fact, our battery model allows us to take into account the aging of the battery. Also, other constraints are keeping constant the take-off mass, which means that the saved fuel will be assumed to be converted in payload. So the reduction of fuel has two burned on the mission has two results. The first one is to reduce the environmental impact. The second one is to increase the payload, which is also important in the air taxi operation. So we, in this analysis, will not consider the reduction of weight along the mission associated to the fuel consumption, because in this application, we notice that due to the short duration of the mission, actually the mass of fuel consumed in the mission is very negligible with respect to the mass of the aircraft. For the energy management of the hybrid electric power system, there is a very rich literature in the land field. So we take from this application this classification, while we can notice that we have two main energy management strategies that can, in order to perform this optimization. The first one is the so-called rule-based control strategies. And the second one is the optimization-based. The rule-based control strategies, we define the power split between the engine and the motor, essentially on the basis of some rules. These rules are based on what? Mainly on the power request and on the battery state of charge, but they can also take into account must take into account, for example, the maximum power and torque that can be produced by the engine or the electric machine. So the physical limits of the components. For example, also the maximum power that the battery can produce according to its specification. So these rule-based control strategies can be based on deterministic rule-based, which means that we can have a sharp transition between one operation mode, for example, with the engine at its highest power, and another mode where the engine is shut off or is asked to work at part load. To avoid such sharp transition, it's also possible to introduce fuzzy logic rule-based control strategies. This kind of rule-based strategies does not ensure that we will have the minimum possible fuel consumption, but they are very easy to implement on board. On the contrary, optimization-based control strategies try to solve with numerical tools the optimization of the fuel consumption, and this can be performed globally, taking into account the whole mission, or instantaneously, taking into account the performing an optimization at each time of the mission. The first approach, global optimization, requires a full knowledge of the future power request. This full knowledge of the future power request is impossible or very difficult in the road transportation, while in the case of aerospace could be obtained, because usually the expected flight is planned before doing it. So it's, however, global, in general, optimization-based control strategies require a large amount of computation to be performed offline or online on the vehicle. So in this speech, we show you the application of this 4 approach to our hybrid electric urban air mobility vehicle. So I'll skip on the details on the application of the single approach because the time is running short, and I'll show you directly the results. Of course, if you want to have more information about each method, I can send you my publication on this topic. As for the results, we have here the analysis of the results of the global optimization. Global optimization is performed taking the whole mission and optimizing the power split in each time by using the dynamic programming method, which is a well-known method of the control research, which is used to find the best possible solution, which in this case gives us the possibility to reduce fuel consumption up to 27% in the case of mission D. What I mean with saved fuel, I compared the fuel consumed in each mission by using the optimized energy management strategy with the fuel consumed using only the engine, which means without using the battery. These results, however, depends on the possibility or not to charge the battery on board, but the effect of this is limited, but above all on the aging of the battery. In this second, I would like to point out that these results are in line with those found in the land transportation. In this slide, we can notice the comparison between the different approaches. So we can say that instantaneous optimization performed with equivalent consumption optimization strategies, which are the green values, are quite similar to the dynamic programming. So it means that the instantaneous optimization is also effective in obtaining our reduction. Also, the fuzzy logic rule-based, which is very easy to be implemented, is also good results. But however, this slide put into evidence like how the energy consumption depends strongly on how we optimize the energy management strategy. Also, as for the well-to-wheel impact, we calculated the saved emissions of CO2, taking into account saved fuel, but also the amount of carbon dioxide associated to the charge of the battery, because during the mission, we partially discharge the battery. To evaluate this, we consider 2 cases. The first one is where this impact is 0 because we assume to use renewable energy. The second case, we consider the electricity mix used in Italy for the production of electricity, the energy mix used for the production of electricity. And so we assumed 300 grams of CO2 per kilowatt hour of energy. And so we calculated the saved kilogram of CO2 per flight, seeing that this amount, of course, depends on the kind of energy used to charge the battery. So to conclude, we can say that hybrid electric powertrains are a viable solution for mid-term sustainable mobility also in the air. But the optimization of energy management strategy is a key issue to obtain the best results. Also, the potential fuel or CO2 saving depends on the specification, emission, and also the age of the battery. And the equivalent consumption minimization strategy and the fuzzy logic are the most suitable for the line implementation, which will be the next step of this investigation. Where we will also try to analyze the urban air mobility in comparison to other to conventional taxis in our towns. So, okay, thanks for your attention, and thanks again for inviting me.
Thank you very much, Professor Donateo. You were perfect in time, and you introduced so much details about your very interesting project. I ask to the audience or to Joy Xu, is there any questions from the audience to your presentation?
Yeah, no, still no questions in the box. But I would invite all the audience, if you have any question, you can just open your mic, just talk to our speakers. That would be more convenient. You don't need to write anything.
I have also I would say maybe a more simple question. If you use battery for your urban flight technology, of course, the weight of the battery plays an important role. So with the weight of the things you transport, the weight of the battery also increases in your different cases. So how do you take into account this development in weight of batteries?
As I said before, in this particular application, we considered the power system as pre-designed. So the battery weight was the same in all cases. We didn't consider different power system. In my previous study, we performed also a multi-objective optimization in order to try to reduce the takeoff mass by but also to have a significant reduction of emissions. So surely the weight of battery is the key issue. But in this particular application, we like to show that it is not the only issue. Once you have sized the battery, it's also important to use it as best as possible.
And what role plays the fuel cell and the alternative technology without battery producing energy on board by fuel cell and hydrogen? Is this also in your investigation still?
Yes, we are. We, in collaboration with the University of Brest, we are also investigating the hybrid electric power system with the fuel cell for unmanned aerial vehicles. In this kind, for example, another important role of the battery is to reduce the dynamicity of the power request. So we can, for example, because we know that the fuel cell is limited in this particular aspect, and so the battery can be used as a buffer of energy together with and so we also, this kind of energy management strategies we're also trying to apply and optimize in the case of fuel cell systems.
So thank you very much again. I was very much impressed how far the developments are concerning this urban air